Hi, in this video, I'll show you the mechanism of multiplying two matrices together, starting with the dot product of two vectors. So by the end of this video, you will know how to multiply two vectors together in a dot product. You will know how to use that to multiply two matrices together. You will learn that there are rules about when it is that two matrices can be multiplied together, because there will be times where two matrices A and B cannot be multiplied together at all, and you will know why. You will also learn that the multiplication of matrices A times B is not commutative. A times B is not the same as B times A most of the time, and you will also understand why. What I will not go into in this video is the deeper meaning of what it means to have a matrix A times a matrix B. This video is about the mechanism only. All right, let's get started with the dot product of two vectors. The dot product is also called a scalar product because what happens is that you start out with two vectors and then you multiply them together and you do not end up with another vector. You start out with vector A, you times vector B, and you end up with a numerical answer, a scalar answer. So it's also called the scalar product. And the way that two vectors A and B are dot product together is pretty simple. Let's say that you have these two vectors A and B, and note how I put the vector symbol on top of the letter A and letter B to denote that they are vectors. When you dot product them together, symbol is one big dot. What happens is just multiply term by term. A1 is multiplied with B1, A2 is multiplied with B2 all the way down to Bn. And once you have all of those products together, you just add them together. So A1 times B1 is a number, A2 times B2 is a number, all the way down to AN times BN is a number, and you add them all together, you get a number, you get a numerical answer. You got a scalar. So A1 all the way down to AN dot with B1 all the way down to Bn is equal to, you take an A term at any row I, you multiply by the B term at the same row I, and you add them together, starting with I from 1 to the last one, I equals n. So it's a scalar answer. Let's do this example. Given vector A is 1, 2, 3, and vector B is 4, 5, 6, then A vector dot B vector is equal to 1, 2, 3 dot 4, 5, 6, and I just multiply straight across. 1 times 4 is 4, 2 times 5 is 10, and 3 times 6 is 18. And then I just add them all together, and then I have 32. So this product is equal to 32. You take two vectors, you multiply them together, and you end up with a scalar. That's the dot product. There's a very natural, real-life meaning of the dot product, and it makes make sense, and that is this. If you imagine that A is the list of prices of three things. So there's some object that costs $1 a piece, something else that costs $2 a piece, and something else that costs $3 a piece. So for example, pencil, pen, and paper. Pencil costs $1, a pen costs $2, and paper costs $3. And if you imagine that B is the quantity of those things, so we're buying 4 pencils, 5 pens, and 6 stacks of paper, then how much are we paying total? Well, $1 per pencil times 4 pencils, $2 per pen times 5 pens, $3 per stack of paper times 6 stacks of paper. So these are how much you pay for each of those items and how much you pay total, all of them, add them together, $32. price vector dot with quantity vector equals total value. That's a very natural interpretation of this dot product. Obviously, it has many other applications as well. Now let's talk about multiplying matrices. Let's take this example. I have a 2 by 2 matrix. It has 2 rows and 2 columns. So it's a 2 by 2 matrix. It's multiplied by another 2 by 2 matrix. And the result of multiplying 2 matrices is a matrix. I call this matrix A. If I multiply A times B, then I get a matrix C. And in this case, matrix C will also be 2 by 2. And we'll talk about the rules of figuring out the dimensions of the answer matrix later in this video. And here's the way it works. In the answer C, the position ij, that means row I of C and column j of C, that position will be equal to the dot product between row I of A dot with column j of B. So at any position ij of the answer, that number comes from the dot product of row I, that row of the first matrix, times that column of the second matrix. Let's take this position. It's the first row, first column of matrix C. So I'm going to take the first row of matrix A, I dot with the first column of matrix B. First row of matrix A, dot with first column of matrix B. Be careful now. First row of matrix A, dot with first column of matrix B. First column of matrix B is negative 5, 7. First row of matrix A, if I'm going to turn it into a column, I have to turn it the correct way. I have to turn it so that the leftmost entry goes to the top. Don't turn it the wrong way around. This is especially true if you come from a culture that reads from right to left. Be careful that the first number has to be the one on the left, not the one on the right. 1 comma negative 2, and I turn it this way, and I'd end up with 1 negative 2 that way. That's the dot product that I'm carrying out. 1 times negative 5 is negative 5, negative 2 times 7 is negative 14, and if I add these together, I have negative 19. So negative 19 goes into that spot. All right? Go ahead and try to do this spot. Press pause and go ahead and work on it using the rules that you've seen, and come back when you're done. All right, welcome back. This position here is on the first row, second column. So I'm going to the first row of the first matrix and second column of the second matrix. First row of the first matrix and second column of the second matrix. I turn this around and make sure you turn correctly. I multiply across and then add down. You got 6 plus 16 equals positive 22. So number here is 22. Right? If you didn't get 22, double check your work and see why it didn't work out to be 22. Right, go ahead and finish off the multiplication for this matrix. Press pause and come back when you're done. Okay, welcome back. I will quickly write down the work for this. This position here, 43. And then that position there, negative 50. Alright, so that's how you multiply two matrices together. Let's look at the general case. Let's say that I have a matrix A with m rows and n columns, so it's an m by n matrix. And then over here on the B, I have p rows and q columns, so it's a p by q matrix, and I try to multiply them together. I will get some large matrix. I don't know the dimension of it yet. Let's take the 1, 2 position, row 1, column 2. Then this matrix C, C1, 2, is equal to row 1. Let's call this A and let's call this B. Row 1 of A dot with column 2 of B. Row 1 of A dot with column 2 of B. That means I have A11, A12, all the way down to A1n, and I dot it with B12, B22, all the way down to BP2 of B. And how do I take the dot product of two vectors? I multiply across and add down, right? And I add. And this is where you realize, oh, wait a minute. What if this vector and that vector are not of the same size? What if one of them is like longer than the other? If B is longer than A, then this A1n is multiplied with some entry in between there. And then what will be multiplied by the last few entries of B? And vice versa, right? If A is longer than B, then after some point you run out of numbers on the B side and the bottom of A doesn't have anyone to multiply with. Therefore, this will only works if A and B, the two vectors, are the same size. This will only works if and only if N and P are equal. And by the way, this is shorthand for if and only if. Going back to the two matrices, you can only multiply A times B if this number and that number are equal. The inside, when you multiply two matrices, M by N times P by Q, then the N and P, the two numbers in the inside, have to be the same number. N has to be the same as P, P has to be the same as N. So let's write that down. We can only multiply M by N matrix times P by Q matrix if and only if N equals to P. For example, if I take a 3 by 5 matrix and I times a 5 by 7 matrix, then it's okay because the inside are equal, then that's good. But if I do it the other way around, 5 by 7 matrix times a 3 by 5 matrix, then that's no good. A 5 by 7 matrix would look like this. This has 5 rows and 7 columns. And I multiply it by something that has 3 rows and 5 columns. And I take this long vector, I try to dot it with this short vector, it won't work. All right, so now we know that if I have M by N matrix and I multiply it by a P by Q matrix, then N and P have to be equal. Let me call this N, because now that we know N is to be equal to P, then I'll just rename this as N. So all the P here become n. All right, let's go ahead and multiply. How many times are we multiplying? For this 1, 1 position, I'm going to take this row. I multiply by that column, so I get a number. The position next to it, I'm going to take the same row of A and I multiply by the second column of B. And I keep going until I get to the end. And that's when I run out, right? I run out of columns to multiply. I take the first row and I keep multiplying by the columns, and I end up with how many columns? Q columns. Okay, let's go back to the first column, first row. Now let's multiply down the column. I take the first column, and now I'm going to multiply out this position, row 2, column 1. Then that means I'm going to need to take row 2 of A and multiply it by column 1 of B. So I get row 2, column 1 here. And then I keep going until the end. Where is the end? The end is when I get to the last row of A and I multiply it by the first column of B. So the end is here, and it's the last row of A, and that is row M. Therefore, all along here I have M rows. I take an M by N matrix, and I multiply by an N by Q matrix, and then end up with an M by Q matrix. So this is how you remember this. To multiply two matrices together, the inside dimensions have to match. It has to be M by N times N by Q. Final result will be the outside dimensions. It will be M by Q. The final result is the outside numbers here. Let's actually write it down as a rule. Rule number 1 is the inside dimensions need to match. The number of columns of the first matrix must match the number of rows of the second matrix. And number 2, the resulting matrix will have the outside dimensions. For example, if I take a 4 by 8 and I multiply by an 8 by 2, then the result will have 4 by 2. Let's take this multiplication. When you're given a matrix multiplication problem, the first thing you should do is check if it's even doable. The first matrix has 2 rows and 3 columns, so it's 2 by 3. Remember, we always say the dimensions of a matrix by number of rows by the number of columns. Row first, column second. So this is 2 by 3. The second matrix here has 3 rows and 1, 2, 3, 4 columns, so it's 3 by 4. That's good. The inside match. And also, we also know what the dimensions of the answer will be. The answer will be 2 by 4. The answer will be 2 by 4. All right, I'm going to go ahead and do one position, and you should try to finish off this matrix. Let me try this position. This position is row 1, column 3. So I'm going to go to row 1 of the first matrix, and I dot it with column 3 of the second matrix. Remember, I read the numbers from left to right, so it's negative 1, 3, 1, and I put it in a column, negative 1, 3, 1. Multiply this, I get negative 2. Multiply this, I have 3. And multiply this, I have another 3. And so it's 4. So number 4 goes here. All right, I've cleaned up the matrices. So go ahead and press pause and finish off the multiplication and come back when you're done. The answer should be a 3 here, 3, 3, 8, 4 on the first row, and negative 9, 12, 4, 17 in the second row. Let's do one more example. These are the same two matrices you saw earlier. But last time we were multiplying 1, negative 2, negative 3, 4 times negative 5, 6, 7, negative 8. This time we're switching the order and we're multiplying. So when we switch the order, we have to double check to make sure that the answer works, right? 2 rows, 2 columns. This is also 2 rows, 2 columns. The inside dimensions match, so it's good. And the final answer will be the outside dimensions, meaning 2 by 2, 2 rows, 2 columns. So go ahead and multiply these. Press pause and come back when you're done. All right, welcome back. This should be your answer. Negative 23 and 34, 31 and negative 46. The previous answer was something else. It was different. If we call this A and B, then you can see that A times B is not the same as B times A. As a general rule, if you can find two matrices A and B that are kind of special, then yes, they will be commutative. But as a general rule, matrix multiplications are not commutative. Let's see if we can figure out the reason why. Let's take the general case of some m by n matrix times n by q matrix, and we should get an answer that is m by q. Well, what is the answer at any given position? At any ij position, it will be row I of the first matrix times column j of the second matrix. So this one here at the corner, the 1, 1 position is going to be row 1 of A dot with column 1 of B. But if you multiply the other way around, if you go B times A, first of all, you're going to have to make sure that the dimensions work out, right? But let's just assume the dimensions work out. Look at you. Then what do you have? In the 1, 1 position, you have row 1 of B dot with the column 1 of A. Totally different vectors. There's no reason why these two vectors that are totally unrelated, row 1 of A and row 1 of B, not related, column 1 of B and column 1 of A, not related. There's no reason why these unrelated vectors should result in the same dot product. Right? So that's why, in general, matrix multiplication is not commutative. All right, so here's a big summary. Hope it helps. Any questions or comments, or if you got some wrong answer and you don't know why, ask in the comment section below. Like, share, and subscribe for more contents, and thanks for watching. Bye.